We've been looking at lateral directional roots. And we had a Dutch roll mode. So we want to analyze that. We want to get its natural frequency and damping ratio because it's a second order mode. So this is the real part. And this is the imaginary part. So the natural frequency from that formula we did a couple weeks ago is that. So if we plug in the numbers, this one dominates, the imaginary part does. Makes sense because it's the frequency, so it would be a major player, especially if it's not very well damped. So that's the natural frequency, and then we need that to calculate the damping ratio. When you do this, make sure you put in the minus number in here for n, and if it's stable, you'll get a minus and a minus, which gives you a plus, because it's a positive damping ratio will be damped, right? So. And so you look at that compared to the range from 0 to 1. 0, no damping, 1, optimally damped. It's lightly damped. And we'll have to wait till the next chapter to find out if that's okay or not. So again, the process of finding all of the dimensional derivatives and then finding the A, B, C, D, E coefficients and then finding the roots is long. So there is a Dutch roll approximation. Where we neglect the roll degree of freedom. And the rolling moment equation. So we're going to solve for beta and psi. Because it turns out the Dutch roll is mainly a side slipping and yawing kind of motion. And there is some bank angle to it, but as an approximation, we can do this. So if we go back to our full 3x3 matrix in the Laplace domain, here's that matrix. Remember how we got this? We took the 3 differential equations after defining the dimensional derivatives, and then we Laplace them with 0 initial conditions. And then we collected them into this matrix. So the Dutch roll is the green stuff. And this sheet should be on your handout, right? Last page in the handout. So you're welcome to mark that up with this on it. Anybody need a handout? I have a few extra. They were free last time, they're $10 today. Anybody else? Oh, I guess I've already got it marked up on there for you, don't I? So you can add colors to it if you want. Seriously, they're not $10. Anybody else want another one? Otherwise, I'll just recycle them. Nope. So if you do that, then you take the determinant, which becomes the denominator polynomial when you do partial fraction expansion. So it's this green thing in the left times the green thing in the right minus the green thing in the lower left times the green thing in the upper right. So you get this determinant. And we can factor an S out of here and an S out of here. And we factor a U1 out along with it. The reason for that is you want to get it in terms of a polynomial with nothing multiplying S. So we're going to take the U1 out as well. So you get the S squared terms come from this thing here and this thing here. And then the S terms come from the NR. And we pulled this S out. Did I lose an S somewhere? Oh, you get it from the NR here. And this term times the S times this, because we pulled this S out, sorry. So we get this thing times this, and then we get this thing times this. Hang on, I'll get it right. So we get this thing times this gives us that, and then the cross product's this times this times this, and then this times this give us the other term. Because those are the S terms, and then all the other terms go over here. And so then we look at this in standard second order form, and this thing here, the whole deal, is the natural frequency squared. And this thing, including the minus sign, is twice the damping ratio divided by the natural frequency. So that's how we get the mode approximations. Right, so that's that thing square rooted, and then this thing is twice the damping ratio divided by the natural frequency. So the damping ratio is that thing in the numerator. divided by 2. So that's the Dutch roll approximation. It's not quite as neat as a short period approximation, but it works. And if we go back to the BizJet and plug in the numbers from that table where we got the A, B, C, D, and E for that, and again, we're doing lateral directional, so you have to look at the lateral directional, but you plug in the NR and Y beta from that table. So back to the BizJet. These are the numbers from page 358. Those are the numbers we've been using all along in our example. And you plug those in the approximation. And there's the natural frequency. And here's the damping ratio. For the approximation. So how do these compare? What did I write for this from the full set of roots? Somebody wrote it down, I hope. The what? It's the same, right? So it compares well. What was this one? So what do you think? Is the approximation good? I mean, it's off by, if you did a percent, it's off by like 25%, which doesn't sound good. But remember, the damping ratio is in a range from 0 to 1. So when you think about it that way, it's not too bad, right? It looks like it's pretty representative of the damping. So it's okay. So it gets you in the ballpark. The reason that you get a little bit different number is that when you're neglecting the roll degree of freedom, this neglects. So that roll degree of freedom includes CL beta, because that's in the rolling moment equation. And we know that's an important stability parameter. So you're losing a little bit of damping from that. So the approximation does not. The other thing we get from this is that this thing plays a pretty big role in the natural frequency, because here we're dividing by U1, and that's a big number. So N beta is an important parameter. And if we look at that, it's this. And we know that this is an important stability parameter. And in fact, it comes from the vertical tail. So that's why we went through all that stuff in chapter 3, is we wanted to say, oh, well, we can look at this and say N beta is CN beta. CN beta is a vertical tail effect. So if it turns out our natural frequency doesn't fit the FAR requirements, then we make the vertical tail bigger or smaller. So this approximation is a real clue as to what you need to fix if you don't get the right numbers. And then how about this? Again, this dominates because here we're dividing by U1, the big number. And this thing is CNR Q bar SB So then we say, okay, what causes CNR? This is a yawing moment due to yaw rate. So the whole airplane's rotating around, right? That vertical tail sweeping through the air. That vertical tail is stopping the roll rate. So again, this is a vertical tail effect. So if you're not getting enough damping ratio in the Dutch roll, you can make the vertical tail bigger. Do you have a question? Oh, okay. So these approximations, again, are design tools where you get a lot better clue as to what's dominating or what's important inside these different modes. Okay, so that's a Dutch roll. The roll mode can be approximated really easily. Because it's just a pure rolling motion. And so all we do is take the roll equation, the one we knocked out to get this one, we just use that one. So let's go back to that Laplace transform. Let me write something on here so it focuses in. Back to this, we keep only the phi, which is the bank angle or roll degree of freedom, and we only use the roll equation. So all we do is grab this center term here. So that's real easy. It says phi to delta transfer function is just that. So we don't even have to do a determinant to get, because we don't have two unknowns, we just have one unknown. So this one's easy. I guess I say solve, but we really don't. We just write it down. And this is an approximation. So this thing is a first order mode, because this doesn't factor into imaginary and real. It's just real. So the roll mode has this time constant. And the root, the roll mode root, remember it's just a single root, is just LP. And the reason the S is here is that, let's say you deflect the ailerons and then put them back to neutral, the bank angle will continue to increase for a while. So you get a little bit of damping. But this is the roll mode, and then the time constant is the negative of 1 over that. So that's the time that it takes to damp to 1 over E. So that's the thing that we quote when we talk about this mode. In a second order mode, we do damping ratio natural frequency. In a first order mode, we do the time constant. And to calculate this, we just need LP, and that's QSBCLP over IXX. And this is the rolling moment due to roll rate, and that's fundamentally the big wings sticking out there and sweeping through the air and damping it out. So this is really a wing effect. And as long as you have fairly decent sized wings on your airplane, then you don't have to worry about the roll mode. It's really well damped because of those big wings. So one of the things that we'll need in the next chapter is we need the response, the roll response to a step aileron input. Because one of the specs says calculate the time to bank to 60 degrees. And that's a function of how much aileron power you have versus how much roll damping you have. So let's do that. Let's put in a step input. Do that over here. So phi of S it's in the Laplace domain, so we just multiply by a step aileron input of delta A. The 1 over S gives us the step input, right? And this is just the magnitude of the aileron. So let's say we deflect the aileron 10 degrees. What happens? Well, this will tell us. So to get phi of t, we'll do partial fraction expansion. And the reason we have to include the s squared is because we got s times s here, so we have an s squared term. We have to include an s term. That's just the rules of partial fraction expansion. Then we have to include this root. And so I'm going to jump to the solution because we all know how to do partial fraction expansion now, right? You multiply both sides by the full polynomial and then evaluate the different powers of s. Or there's various other ways of doing that. But we get a Laplace response and then a time response when we inverse Laplace. So if we inverse Laplace this, here we're going to get a t term. Here we're going to get a step input term. And then here we're going to get an exponential term. Right, inverse Laplacing. And the A0, A1, and A2, we'll have to figure out what they are. So we inverse Laplace, we find out A0, A1, and A2. And the time response then, once we do some algebra, So there's the term, the t term that comes from the s squared term. There's the step response here that comes from the us, and then here's the exponential term from inverse Laplacian. And what it says is that if you kick in a step input aileron, so we put in like 5 degrees, this term says it's going to continue to increase in bank angle. Makes sense, right? You're flying straight level, you kick in some aileron, the airplane's going to start to bank, and the only way you're going to stop the bank is if you take the aileron out and allow it to damp out. Or do reverse aileron to stop it, but then you got to let back off to neutral to hold it where it is. So you get a steady state roll rate with an aileron input, which is what really happens. All right, so we'll use this in the next chapter to calculate the time to bank to like 60 degrees and various other requirements that we need. Notice again that it depends on the aileron power. That is, how much power, how much roll do you get out of your aileron? And then this is the roll damping. The more roll damping you have, the less the ailerons give you a roll. Let's see, we need to calculate the bizjet for this. So the bizjet now, I'm just going to calculate the time constant, or actually just the root. So for the bizjet example, the approximate formula, if we plug in all the numbers for LP, and then we compare that to the full value. Well, wrong number. Go back and look at that root. It was like 0.5 something, right? When we did the full 4 degrees of freedom, it was 0.5003. So this is not a bad approximation. And then typically, again, if you have big wings, you get big LP and you get good damping out of this thing. All right, last one is the spiral mode. That's another mode that we'd like to be able to approximate. So it turns out that you can approximate this as a gradual banking and a gradual side slip. And so we're going to neglect the side force equation and solve for beta and psi. So we knock out the roll equation because that's all in the roll mode. Same process, we go back to the matrix. I think by now you get the idea, right? You look at this matrix and you say, well, what equations can I knock out for which mode? And in this sheet, my blue marks aren't showing up, but they're identified in the handout that you have. So we keep the L beta term. Again, we're knocking out the roll degree of freedom, so the middle column goes away. And the, sorry. Yeah, we're throwing out the side force equation. So the middle column goes away and the top row goes away. Get rid of the side force, keep the roll and the yaw. And so we get another determinant that then gives us the mode approximation. So we're going to grab this term here, this term here, this term here, and this term here. And if we factor an S out of this thing, and then this is our first order mode here. So again, the spiral mode is just one real root. We get it from this thing here. It's kind of a mess, but it's better than calculating all those coefficients. So there you can calculate the spiral mode. And for the BizJet, plug in numbers. Compare to and it looks off by a lot, but again, it's 0, 0, so it's a right order of magnitude. So part of what you're doing in your homework is calculating real roots. I'm sorry, calculating the full set of roots. And then you're also calculating the roots from the state space form. And you're going to calculate the roots from the approximation. So on Blackboard, I've given you the solution for the state space, so you have a place to start. So this is what you need when you're calculating the roots in that homework set from state space form. And again, this is uploaded to Blackboard, so you don't need to write it down right now. And this should have been what you got for the answer when you did this homework that you just turned in. So make sure you grab that before you do the homework that's due. It told me my microphone changed. Can you guys still hear me? Okay. I don't know why it said that. So for the next 10 minutes or so, we're going to start talking about flying qualities and pilot ratings. So this is chapter 6. Yeah. Yes, it did. Why is it doing that? Switch back. Yes, no. You guys hear me on Zoom? I'm sorry, what? It's still using the mic. How about now? We'll see how long it lasts. I keep thinking maybe somehow the battery's dying, but I got a blue light. All right, let me know if I drop out again, all right? So chapter 6 is on flying qualities and pilot ratings. And fundamentally, a lot of this has to do with the fact that you want the pilot to be able to achieve whatever mission, flight mission, with physical effort, that is control forces, and mental effort. You don't want a high workload. And the key is that you want the pilot to be able to do that in different flight modes. Obviously, it's important to have a good workload environment at takeoff and landing, but also in cruise for a civilian aircraft. And then for a military aircraft, takeoff and landing, ground attack, combat, and intercept, we'll need to analyze the flying qualities, the flight characteristics of the airplane in all of these different flight modes. So you'll see that we'll quote, well, is it a civilian aircraft? Is it a military aircraft? Where is it flying? What is it intending to do? What flight category is it doing? And what airplane category is it? One of the ways that the ratings that I'm going to show you were developed was by pilots flying different aircraft and then doing what's called the Cooper-Harper rating scale. I'm going to zoom out so you can see most of it. So the pilot will go up and fly an aircraft, and then he'll start down here at the bottom with the arrow, and he'll answer these questions. Is it controllable? If he comes back and says, man, I barely got it back on the ground, it was horrible, then improvement is mandatory and it has major deficiencies, and it gets a 10. Now, sometimes you'll see this chart flipped around where a 1 is bad and a 10 is good, so make sure you pay attention to the chart. And then he goes up, if it's controllable, is it adequate with a tolerable pilot workload? No, then it gets a 7, an 8, or a 9 based on how bad the flying qualities were. And is it satisfactory without improvement? And the best rating is the top. It's excellent. It's highly desirable. So the pilots rated different aircraft with different stability characteristics. And then the requirements were developed so that people designing airplanes could say, okay, if I meet these requirements, I know that I will get an airplane that gets a good Cooper-Harper rating on it. And the regulations are in various specs. There's mil specs, and then the various parts. So let me just write those on the board real quick. By the way, all these overheads I'm showing you are in the book, in the chapter. So the pilot ratings have been, and specs have been combined into various documents. And this is referenced in your book. So if you want to, you can look these up. And typically the mil specs are a little more stringent than the civilian specs. Part 35 for heavy aircraft, 25 for medium, and then 23 for lighter aircraft. And this is in reference 6.3. And there's also some very light aircraft specs. And then the aircraft class that you'll see in these charts will classify the aircraft into various different categories. So we will say, in an example, we'll say, okay, the BizJet is a class 2 aircraft flying at this condition. So here's how those works. So this is on page 418 in your book. So class 1 is small, light aircraft, like a Cessna 182 or a Cessna 210. And these would fall under part 23. And then you got class 2 aircraft. So these are medium. Weight, this is like a Boeing 737, and that's part 25. Class 3 are heavy. Large, so this would be like a 747. They're in part 25. And then class 4 is more military. It's highly maneuverable. Like an F-15 or an aerobatic airplane like the Pitts Special. So again, you find out what airplane you're dealing with, you categorize it into a class, and then you look at, well, what's it doing? Is it cruising? Is it taking off? Etc. Let's see, we did the Cooper-Harper. So I've written some general categories up here. Your book gives a much more detailed, and it's kind of fun to look at, I think. Let's see. So let me rotate this. So it shows some more examples of the class aircraft, class 1, part 23, like the Cessna, the Beech, T-34, small light, class 2, whole bunch of airplanes here, so you can get an idea. These fall under part 25. Part 25 for the large aircraft or the big stuff, like the 747. Then highly maneuverable, like a fighter, interceptor, attack, tactical reconnaissance, trainer, or observation. Wouldn't the what? Yeah, yeah. For some reason, when you said it, I was picturing a Citation jet. I don't know why. My mistake. And then we look at flight phases. So once you categorize the aircraft, then we'll look at a flight phase. So all the way from engine startup and taxi to takeoff, accelerate, maybe dash. This is for an attack aircraft. A steep climb. So we'll identify the flight phases. Takeoff, climb, cruise, descent, approach, and landing. For a passenger transport, it's a lot simpler. You taxi, you take off, you climb, you cruise, you descend, and land. And the flight phases are categorized into category A or B or C. C are the terminal flight phases, and I never liked that word, even though it means terminal, like where you're terminating your flight. Terminal always sounds like terminal illness, right? Like you die. So, but the terminal flight phases are category C. Category B is non-terminal flight phases that are usually not real precise, like climb, cruise, loiter, descent, parachute drop, various things like that. So you're up there and it's not a high workload environment. And category A is precise flight path control. And some of these are kind of fun. Anti-submarine search, obviously weapon and delivery, ground attack, you need precise control. But look at this one, fish spotting. I never would have thought of putting that in this category, but evidently finding fish is precise maneuvering. Pipeline spotting. And then another category that we'll talk about are what are called levels of flying qualities. So once we identify the airplane and what's it doing, then we want to see, well, how well does it satisfy the requirements? And there's several different levels for that. So these are mil-spec quality levels that most even civilian aircraft go with. And so level 1 is the best. It's adequate. For the mission. So that's what we shoot for. Level 2 is adequate but higher workload. And then level 3 is much worse. Safe control, but excessive workload. So as we go through the BizJet examples, which we'll do, that'll probably be our first online lecture. we'll look at, well, does it meet level 1 or level 2 or level 3 in the categories? Last thing for today is kind of a weird chart. Only because you look at it and you expect it to be an XY plot and it's not really. But with regard to aircraft flight safety, flight critical components, you'll hear people talk about 10 to the minus 9th. And often they'll say it without saying anything more, and you're just supposed to go, oh, yeah. So what this really means is one failure in 10 to the 9th flight hours. So it's a probability. The probability of failure is 10 to the minus 9th. So that's what they're meaning when they say, okay, the mechanical flight control system has to satisfy 10 to the minus 9th. It means only less than one failure in 10 billion, right? Yeah. No, 1 billion flight hours. Which sounds like a lot, but when you look at the number of flights hours there are every day, the number of airplanes that are up there, this is maybe not quite as restrictive, or not quite as restrictive as it should be. So anyway, the chart that they have in the book that will be confusing looks like this. So it looks like there's a vertical scale and a horizontal scale. But notice they say no scale intended. So what it's really saying is that if you have a failure, but it would not impair continued safe flight and landing, it can have a probability of happening of like 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, depending on what the effect on the airplane is. If it's no big deal, it can happen as many as 1/10 of the time. If it's a nuisance, it needs to happen less often. If there's emergency procedures, but you can still handle it, and it needs to happen less often. And as you go further this way, you get to the point where failure conditions would prevent continued safe flight and landing, which means you crash. And that's where you want the 10 to the minus 9th. So as you go across, you want the probability to be less and less because the failure will cause more and more bad things to happen. That's it for today. We'll continue on with this next time. Yes. So make sure that you're available for lecture on that Tuesday when we come back. Tuesday and Thursday. If we finish on Tuesday, I'll let you know on that day.